Okay,
thank you.
What you see here is the Dachstein, the highest mountain in Upper Austria some years ago. And maybe you can see a small track where I was going along with my skis here. And in the summer when I came there was a huge crevasse. And if I had foreseen this in the winter time, I would have taken another track. So sometimes it's really good to see below the surface. And when we can do this without removing all the snow from below, from above. But of course, we do not do this for crevasse, but usually we use it for voids and or for other, for delaminations and to look under the surface. Yeah, and yeah, maybe you see this, you have seen some similar pictures in the past. Here it's called in German mit Röntgenblick and Laserauge, and with this this guy Victor Filippi claimed that he can look into materials and into persons, but we can do this in reality. I have just shown two videos. One is from optical coherence tomography. You see, you can look into the form and see the different wall thicknesses of the bubbles. Or another example here on the right side for a carbon epoxy material where you can see the individual fibers. And mainly we use infrared light, the near infrared or also the mid-infrared light up to the far infrared, which is also called to the terahertz. So that's our spectral range. Yeah, and together, just how do we get the information out of the material? Just a simple example, when you have a drop of water on the water surface, you see that the surface waves are spreading out, and if you measure these waves, you can detect the individual location of the drop or how thick the drop was. So what we are doing is we use sensors, we use signal processing, and we use simulation, so we have to use a model for that. And with all three, with this 3S, we get our information. So that's just for all our measurement principles. But let's now come to tomographic imaging. In tomography, you usually will see it later from Günther Mayr, also from the Fachhochschule Wels, that we use an infrared camera with about 1 million of detector pixels, and this is contactless. In ultrasound, we have about 100 or several hundred detector elements, and usually for ultrasound, you use a coupling media at water that you can also look into the material. And what we are trying to do is we try to connect the advantages of both methods, and we use a thermal image, a thermographic image, and use some transformation to get an acoustic image out of that. That's called a virtual wave image. And with that image, we can do acoustic reconstruction. So we can combine and marry both technologies. Just to see what happens when you have a laser pulse, for instance, from a laser pointer on the surface, then the surface will be, the light will be absorbed at the surface. It will be heated and you will get some thermal diffusion into the material. But at the same time, because of the thermal expansion of the surface, you will generate in elastic waves an ultrasound wave. You can see it here. Both, here's the thermal diffusion, you see the temperature, and here you see the pressure. So the elastic wave goes down, is reflected at the back surface and goes back again. And both of these phenomena, the temperature, the heat diffusion, and also the acoustic wave have the same source. This is the heating of the surface here. And from that, you can do this, of course, not only in one dimension, you can do it in several dimensions. Here we have again a laser beam. which penetrates, for instance, blood, tissue, or also epoxy material, and it heats the absorbers here, for instance, some blood vessels or some carbon fibers, and these absorbers are heated. And because of the heat, they send out the heat. The heat is spreaded and can be measured at the surface by an infrared camera, or because of the thermal expansion, they send out an ultrasound wave, which you can also detect. And both technologies can be used. Here, the first one is called the photothermal computed tomography, or the second one is the photoacoustic tomography, where both can be used to detect what is inside. And especially for the thermal signal, we have heard before that it has some advantages. Especially for the thermal signal, you have some heat, you have the heat diffusion, and you have some spreading, and information is lost because of the diffusion, and therefore it is not so easy to reconstruct the structures which are below. And in the next slides, I will tell you how this can be done. So maybe I have to move this a little bit, so now it works better for me. What I have told before, when we can take an image with an infrared camera of the temperature, of the surface temperature, let's call this temperature T here. And we can transform it to a so-called virtual wave. Here's the mathematics, but in a discretized version, it is very easy. You have just one vector T, you have a matrix K, and you have the virtual vector T vert, and this is a function of time, the temperature, and also the temperature here. The virtual temperature is a function of time, and both can be converted by the simple equation. We can see it here, a small example. You have here the depth, and you have the surface. It's a two-dimensional cross-section, and you have because of the heating with the laser light or with another light source, you have here this temperature sources. And if you measure at the surface the temperature, you will see something like that. You have here the time now, and again the surface extension, the pixels, and you see from that the surface diffuses very fast, and also you measure quite a high temperature. But the others are very, not so good to see. If you take this relation and you invert this K, where you need some regularization methods, then you get the virtual temperature, and the virtual temperature you see looks like an ultrasound signal already. So you see this hyperbola because of, and also you see the blurring of the deeper ones. And then you can use an ordinary ultrasound reconstruction method like FSAFT or time reversal or whatever you like, which is very well known from ultrasound techniques, and which that you can reconstruct the images again. You see the initial temperature. And my last slide, before we go to really practical applications with Günther Mayr, will be just to show you first a one-dimensional example. You have absorbing layer in a resin. The resin is opaque for the light, so it can be heated, and then the heat diffuses to the surface, and you measure with the infrared camera. And for infrared light, this material is not opaque. First it was transparent, and for the infrared light, this is then opaque, and you only measure the surface temperature. And when you measure the surface temperature, you get something like that. So for a depth of 7 millimeters approximately, you get this. For a depth of 11 millimeters, you get this temperature evolution. And from that temperature evolution, you can calculate the so-called virtual wave. Here I have shown two different methods. The first one is an ordinary method called truncated singular value decomposition, and the other method is a more advanced method where you use also additional information like sparsity, that you only have a small layer, and in in the cross section, it's just a peak, and you see that you get a much better reconstruction with that. So with that, I just will give you a last picture here, that you can do it not only from one side, but you can do it from several sides. And this is called photothermal tomography, because you can use the photothermal technique from that side, and from that side, and you can combine these results, and this helps you to really reconstruct what's inside, also at a higher depth. So, and now I try to get the other. So the second one. This is this one. Yes. Of course. So. And we have to move this one. Okay, perfect. Please, Günther.
Yeah, thank you very much, Peter. Yes, hello. My name is Günther Mayr from the Upper Austrian University of Applied Sciences, and it is a pleasure for me to show you today the practical applications of the so-called virtual Wels thermal tomography. Yeah, let's start with some practical applications. Here you can see the very important industry for us, the aerospace industry. In this industry, there are a lot of different materials used, and the most important for the non-destructive testing technique, thermography, are composites. You can see here on the left side a practical application. This is a turbine housing. This turbine housing is made by people. And so it is sure that there always occur some defects in the manufacturing. And as this is a safety critical component, it is necessary to do some non-destructive testing at the end of the production. And you can see here on the right side the very emerging technology of active thermography. You use an infrared camera, and you also use some excitation sources so that you can heat the surface, and the heat propagates into the material. And at interfaces, there is some reaction to the heat flux, and there's some back propagation to the surface, and you can measure temperature contrasts in a non-contactless way. It is an imaging method, and it is very fast and cost efficient. In the year 2017, the first technical qualification was given from Boeing for this non-destructive testing methods. And in the last year, we also get the technical qualifications from Embraer and also from Airbus this year. Yeah, this is our equipment at the University of Applied Sciences. We have different quantum detector cameras and also some microbolometers that are the best cameras on the market up to now. Here you can see we have a camera with a very high spatial resolution. That means we have more than 1,000 detector elements in each direction. But we also have very fast cameras. Here, this high-speed infrared camera with more than 1,000 frames per second. The other ones are very cheap cameras for some industrial applications, and also we have the possibility to do some spectroscopy with this camera with some filter wheels. Yeah, on the other side, we need some excitation sources for active thermography. There we also have some different optical sources. Here you can see a classical setup. Here we use halogen lamps for a very large scale excitation of the surface. We also have some flashlights for a very short pulse, but we also use some lasers for the excitation of materials like metals, where the absorption coefficient is very low. And we also do some automation developments. Here you can see our test rig and translation and rotation, but we also use some robots for the manipulation of the sample or the infrared camera. Yeah, there are also some different measurement configurations in active thermography. You can see here the most typical ones. On the left side, it is called the pulse echo or reflection configuration. You heat it up the surface and the heat propagates into the material, and there you have some interactions with the defect. That means you have here the heat or the temperature increase on the surface and then the cooling down behavior. And when there's a defect, you get some temperature contrast. Similar, it is in transmission configuration. You excite on the back surface and measure on the front surface, and you also get some typical temperature curves, which gives you some information about the defects inside the material. The last one is some internal heat source. In this configuration, we use some eddy currents to heat up electrical conductivity materials inside the part material, and here the heat only propagates from inside to outside. Yeah, the first is some scientific sample or phantom. You can see here an epoxy cube with 3 inclusions with 3 graphite bars, and this material is opaque for the infrared radiation. So that means you only measure the temperature on the surface. And when we now use some heat source, in this kind we use some laser excitation, then you can heat it up the internal structure, these graphite bars. So you have 3 different internal sources. And on the left side, you can see the process or the mechanism of the virtual wave concept. You have 3 different internal heat sources. You measure the surface temperature over time. This is the surface, this is the time axis. And as said Peter before, you have a very good temperature contrast for the nearest defect, and it is better for the deeper ones. And now we use the very fast and very strong algorithms of ADMM. That means we use some sparsity and positivity for the regularization. You get this typical ultrasonic Schallgeberbe, Schallgeberbe of English.
Sound hyperbolas.
Sound hyperbolas. And when you have this sound hyperbolas, you can use the ultrasonic reconstruction techniques to reconstruct these internal defects with a very high resolution. Yeah, the next one is a more practical example. This is composite material with different thermal diffusivities in each direction. You can see here the sample, here the excitation sources, and here the infrared camera. This is the description of the sample with 3 different flat bottom holes. And these are the dimensions. The diameters goes from 4 millimeters up to nearly 12 millimeters. We have different depths and different ratios of the diameter to the depth. And now we try to reconstruct the position and the depth of these flat bottom holes. And you can see here the results. Here in the first row, you can see the temperature image of these 3 defects, and you can see that you're not able to indicate this defect only with the temperature signal. In the second row, you can see the virtual wave signal. You can see here a much better feature extraction as with only the temperature signal. And when you do now some ultrasonic averaging techniques, you get a very fine and a very good contrast with the real defect shape in this result image. And this is the top view, and here on the right side you can see a cross section, and also you can see here the very good reconstruction result with a very high accuracy dimension of the defects. Yeah, and with the virtual wave concept, it is called tomography. You are also able to do some 3D reconstruction of these internal defects. And this is the first time worldwide which makes it possible to do this 3-dimensional visualization of the internal defects by temperature data. And this is also very fast, only 1 minute for the calculation of the whole image. A very high benefit you have when you apply this technique by unidirectional samples, because you have a very high thermal conductivity in the direction of the fibers. And you can see here again only the temperature contrast image. You are not able to distinguish between the defects clearly. You cannot see this very deep flat bottom hole. When you do now the first reconstruction step, that means the virtual wave signal, you get a very good contrast, but you are not able to discretize between the 3 defects. And when you do now some reconstructed methods from ultrasonic testing like FSAFT, you are also able to identify the 3 singular flat bottom holes with a very good correlation to the real defect size. Yeah, now the last sample, it's some fatigue damage. When you have some tensile load on your composite material, like here, you have here the tensile test machine, you have some hole inside the sample, and then you use some fatigue testing. Then you have some different defects. That means some interface defects, matrix cracks, and so on. And you want to do now some inline testing to see how this damage is increasing with increasing load cycles. Yeah, we did this in this experiment, and you can see here on the left side the cross section of the sample, the reconstruction of the virtual wave. And you can see as you increase the cycling numbers, you have an increasing of a damage size. And this is fully an in-service application of active thermography. Yeah, I want to show it. Here it is on this small video. So now you have 12,000 cycles, and you can see in this top view how the defect increases its size. And you can monitor the damage behavior in an in-service application. And you also have a very good resolution with this method. We have a zeta vector resolution of about 20 microns, and then the in-plane direction of about 250 microns. Yeah, with this I want to sum up my talk. The virtual wave concept was applied for 3D defect reconstruction in anisotropic samples. We can reduce the computational cost very dramatically by optimize the discretization of the kernel and to use the optimal measurement time. The feature extraction capability of the virtual wave concept is much better than in the temperature field, and you can find really more defects as when you only look at the temperature data. And at the end, the incorporation of the bioinformation, as Peter said before, that means sparsity or positivity, you can increase the spatial resolution very significantly, and this allows to increase also the field of applications in the aerospace industry. And with this, I want to finalize my talk, and thanks for your attention.